Welcome everybody to the 3D scanning and motion capture lecture. Today we're going to continue with face tracking and reconstruction. And I would like to start with a short recap where we have left before. We've generally been talking about 3D reconstruction. Then we've talked more about dynamic 3D capture. And specifically we talked about the differences, how you regularize the dynamic capture, right? So we started with freeform tracking and freeform reconstruction. And then we moved to more domain-specific thing, and specifically we started talking about human faces. And the idea here is, what we did in the last lecture is we talked about how can we create a parametric face model. And the idea was that we want to construct a face model such that with a relatively small number of parameters in our face model, we would like to parameterize the model, and we would like to create this controllable kind of like avatar which we can use to re-render new images. Now, more specifically, here we see the example here. This model basically should be parameterized according to the shape, to the albedo variation, and also with respect to expressions. And later we talked a little bit about lighting and pose as well. So we talked a lot about how to reconstruct this model. And at the end of the day, when we reconstructed it, we get something like this. So here we have this parametric model. So now we have a couple of sliders, which is essentially this lowering approximation with the PCA, what we talked about. We can use it in order to control the shape. We can have another set where we can control the albedo, and we have another set we control expressions and also lighting and so on. And at the end of the day, we have these parameters here, right? So we have alpha, beta, delta, gamma, and the rotation and translation. So we have the geometry, albedo, expression, illumination, and pose parameters. And all of these parameters together right now parameterize this face model. And we spent a bit of effort going through all the details, how we create it, meaning that we started with the data capture that we need in order to create it. And then we started with the math, like this PCA basis essentially for the geometry and the albedo, and then the delta plane shifts for the expressions, and Spherical harmonics for the illumination respectively. Okay, now this was all fun, right? It's kind of cool. Now we have a parametric face model, but today we want to talk about what we actually do with it. And more specifically, we want to use these face models right now in order to face tracking and face reconstruction. Now, if we are considering we have this 3D face model, I touched this at the end of the last lecture, what we can do now is we can take this 3D face model, we feed in a bunch of parameters here as input, right? So these parameters plus the parametric model, they essentially determine what kind of 2D image we can render or what image is being rendered. This is an image formation model, right? So the model plus its parameters tell me what kind of 2D image we're getting. And that's kind of a really powerful thing because we have this image formation model right now. And our goal at this point is we want to invert this process. So rather than taking the model and create a 2D image out of it with the forward rendering process, we now would like to go ahead and take the 2D image as input, and we would like to reconstruct the 3D face. And reconstruction, to be more concrete, in this case means to estimate and optimize for these parameters of the model, meaning that we want to optimize for pose, shape, albedo, illumination, and expression, right? And the core idea is that this model right now is serving as a regularizer, right? So if you wanted to parameterize very naively a 2D image, you would have a way too complicated distribution. So in a sense, this model here makes it a little bit easier with a relatively small set of parameters in order to describe this image formation model, where if we're feeding in these p's, we're getting the original image that we fed in, right? Again, so this is what we want to do. Give me a 2D image as input, and I'll tell you what the parameters p in the output are going to be. Now, here I said the input is a 2D image. We'll later see a little bit, it's probably not only one image, it could be multiple images. It could also be a combination of 2D images and RGBD. So we might have depth or we may have not depth. We'll talk about this a little bit in detail, what this means in practice. But for now, I want to continue with this image formation model idea, meaning that the goal here is, right, that this model plus parameters determine what kind of image we have. And this essentially allows us a way to invert the process of the rendering and do the reconstruction with an analysis by synthesis idea. And the way how this works is essentially we have a 2D input image. This here is our input image. And what we can do now is we can just take, I don't know, a random set of initial parameters p. We're taking those ones. This is our model right now that we can synthesize with our initial set of parameters P. You can see it doesn't look like this one here, right? It's just some random overlaid face. It's already overlaid to a reasonable degree, but it doesn't really have any of the features and traits what the original face here would have, right? So this is starting with an initial parameter set P, and what we can do with that is we can render it, and we overlay this rendering on top of the original input image, right? And now what we do is we compare this re-rendering with the original input image, and we will notice, oh no, we made a mistake, it doesn't look exactly the same, and we try to minimize the difference between these two images, and minimization here is essentially optimizing for the parameters of the face, right? So we want to make this one here look like that one by changing the parameters P accordingly. And the way we're doing it is we rendered it with an initial set of parameters P, we compared it, we realized, oh no, it was wrong. Let's update our parameters accordingly. And then what we do is, well, we get an updated set of parameters and we re-render it again. Okay, now we re-render it again. And now we have an updated parameter set P, and our rendering looks already a little bit better than before, right? So after one iteration here, we already get a better re-rendering. And now in principle, this one here looks already a lot more, this one here looks already a bit more similar than this one. So the pose here is, well, not perfect, but it's already better than before. And now we do the same trick again and again, right? And we iterate. So we have this analysis by synthesis. So now we do the same trick. We render this one, compare the differences, parameter updates, synthesize again, and so on. And this is what we do. Okay. Next step, you see, now we get the albedo already right to some degree. It's still not perfect. You see that, you know, it doesn't look that ideal yet. We go again. It gets a little bit closer again. Go again, a little bit closer, and so on. And now you see this still changing here, right? And now at the very end of the day, we're happy and we see that this image here looks pretty close to that image. And then we're done. Then we have found our final set of parameters, right? And this is an optimization process. It has kind of this renderer here in the loop, right? So we render the model, we compare it with the input, we find some updates of the parameters, we re-render again with the new parameters, and so on. So because this was so nice, I'm going to just show this animation here again. We started here, render, update, render, update, render, update, render, update, render, update, and we're done. Okay, now this is a process for every time we have re-rendered it, there's a process where we have to figure out, well, how do we update the parameters? And I kind of conveniently glanced over and said, oh, we just look at the difference between those two images. But in practice, it's actually not so straightforward. And this is something I would like to talk about in the following, because essentially what we have to do is we have to find gradients. So this is a gradient-based solver that figures out the differences between these two images, and based on the differences, compute some gradient with respect to the original model parameters, does a model update, and so on. Okay, so now we have to think about, first of all, what is our input, what we're comparing against, right? So in the previous animation here, I showed you basically one single image, and I said, well, we render it and we compare this one single image, and that's it, right? That was it. Okay, but in practice, we have a couple of more options, right? We can have a single image, what I've just shown you. We can have a webcam, which is a bunch of images. We can have YouTube videos. We can also have Rgb data from a Kinect, right? And these are a couple of examples here, right? So we can have RGB, we can have depth. And now what we want to do is we want to go ahead and basically take, this is the GPU here, right? The GPU is supposed to be the rendering engine here. So we take these parameters P here, and we render it, we feed it to the GPU, and then we're getting some rendering here as output. So right here you get the texture mesh, and here we just get the depth basically. And this is what we have to compare right now, right? So we have to compare whatever we have as input. We have to compare with whatever our current set of parameters P is rendering once we're feeding it to a rendering pipeline. And again, there's different types of renderers. In the following, we're just going to use a standard rasterizer, and I'll explain to you in the standard rasterizer how we use gradients and how we get them and so on. But in principle, there's multiple options how to do these kind of renderings. You could also use a ray tracer. There's a couple of cool new methods that have come out very recently that could be used here, and so on. Okay, but let's stick to the standard graphics pipeline right now. This is a standard forward rasterization. This is basically what OpenGL and DirectX also would do for you. And now what we want to do is we're going to compare these two things. And we're just going to formulate an energy term here. And this energy term is a term that compares literally every pixel on this mask and on this mask here with the counterparts in the observed data, right? And we're calling this a dense term, but in practice, these are actually two terms. There's a color term, which is this one at the bottom here, and there's a depth term at the top here. So we have a dense depth and a dense color term. And what we want to do here is we want to figure out what are the optimal parameters P, this P star here, such that we minimize the distance between those two, right? And again, just to reiterate it, these parameters P here are all of the parameters of our phase model, right? So we have, again, geometry, albedo, expression, illumination, and pose. And these are the unknowns that here in this optimization we are solving for. Okay, so let's have a look how it goes. Okay, one thing we have to think about is there's a couple of challenges in practice to make this stuff actually work. So if you're just using these comparisons here, you will notice that, oh, here we already have some reasonable overlap, so we're close enough. And we have other things we can also leverage. We can also leverage, well, it's kind of a phase model. It's probably not going to be too far from the average phase. So don't go too crazy on the deviation of the average P parameters. So, and this is something that you typically do as a whole optimization problem. And we're going to talk about this energy here for a little bit now. So I've just talked to you already what this dense one is going to mean. This is our data term based on the input images and then the input depth maps. If we have depth maps, talk about we may or may not have depth maps. There's typically another sparse term. This sparse term is a term that takes a bunch of landmarks, facial landmarks, in order to get some initial alignment. And we're going to talk about a regularization, which says, oh, kind of make sure it's a reasonable phase. So this is our prior from our model. And this is the data term, and this is the priors. So if you remember from the non-rigid deformations and the non-rigid optimization, this is very similar right now to what we have seen when we did this deformation with RRAB or ED, right? So very simple thing. These are our data terms, and then we have prior terms. Except here on the prior, we have our phase model now, and for our data terms, we have the difference between the rendered RGB and the rendered depth maps, and possibly some landmarks from the sparse term here. Okay, so let's talk about the dense terms first, because that's the interesting thing. I already mentioned the dense terms is basically two parts. We have a color term, and we have a depth term. And what we do is, it's relatively straightforward, right? So we just say we have two images. We have the image of the input. We have the image of the rendering. And what we want to do is, we want to simply go over every pixel. So we're summing over all the pixels here. So these ones have the same resolution. So we're just checking, is this pixel minus that pixel the same color? Is that pixel minus that pixel the same color, and so on? And that we're just summing all of this up, and we're trying to minimize that term. Now, since what I've just told you would mean that we're summing over every pixel here, that would be a little bit premature because we would also consider the background and so on. And the background is actually not even part of our phase model, so there's no background here, right? So in practice, what you do is you just sum up over all the pixels on the rendered phase model and then check out in the image here what's the corresponding pixel value, what we have rendered here, right? So this loop here, or this sum here, goes over every pixel here on the phase mask, and the rest is masked out. So we're only using the ones that are actually interesting and relevant. And then what we do is we compute this difference. And based on this difference, we have an energy. And what we would like to do is we would like to minimize this energy and get essentially a very, very small reconstruction error. Okay, so this one is the color term. And in fact, we do the same thing for the depth term. So now again, we have a loop. We have the same sum here that goes over all pixels on the phase mask. And we compare it with the respective depth measurements that we have observed in the respective, the corresponding pixel from the input. Okay, so Let's talk a little bit about how this is done in more detail. This is actually still not so straightforward. So the measurement here is typically in pixel space. So we take every pixel and we measure in color space. And here we measure in world space, which is just take the 3D values and make a difference. But it's not as easy. So let's talk about the first part here first, the color differences. This is actually, there's a lot of research how to do that. And there's a few things you can do to improve this and to make it a little bit more robust. So generally speaking, this is a photometric term, right? So we're just saying, okay, compare every pixel on the face mask with everything you have observed. What we can do is we can just measure distances in RGB space, right? So you have RGB, and you take a 2 norm between the two and try to measure the difference between those two. That's one way to do it. You can, however, also take other color spaces. You don't have to do this in RGB space. You could do this in HSV space, in lab space, and so on. And each of these spaces have slight advantages and disadvantages depending on the spaces. I'm not going to go into all the details here because this is in a sense very similar to what we have seen already for the bundle adjustment works like bundle fusion and so on. They kind of have similar ideas where you also take differences in color spaces and you can use different color spaces. The other thing what you have to consider here is there's different norms you can use. So you can use a 2 norm between every pixel. You can also use an L1 norm between every pixel. You can even use any other norm to compare the color values. You can even use gradients to compare it to get a little bit of more robustness towards white balance changes and so on. But the bottom line is there's a lot of different things you can do to compute this photometric term. I don't want to provide the definite answer here. There's a couple of different versions of it. I just wanted you to be aware that there's a few options that you can choose from depending on what kind of setting you have, what cameras you're using, and stuff like that. One thing that is also important is not just the camera setting is important, but it's also the optimization is important. So if you're using an L2 term is like really great for optimization because you can compute very nice gradients later on. L2 term, not so hot on outliers. If you have a few outliers, the L2 terms are pretty bad. Remember when we talked about robust optimization and so on? This is essentially what you could do here as well. So it's a bit of a compromise, like how expensive and how hard is the optimization to do versus how robust and how nice the photometric term is being conditioned. There's a little bit more to it. You can also do some convexification. One problem you're going to run into if you have photometric terms, generally speaking, they're super non-convex, right? So imagine you have like a checkerboard pattern and overlaying it and you're off by like 1 grid, right? You're always going to converge to the wrong offsets. And this is something you have to consider in practice. Again, some of the things we have already talked about in previous lectures, but again, I want you to be aware that there's different options how to deal with these kind of things. Okay, so with the depth, it's a little bit easier, and we also have talked about most of the things. There's not that many options in practice. Okay, so in practice, what you do is same thing, right? You take every pixel that is on the face mask, you're projecting it, or you're looking up the respective depth values in the input depth map, and then what you're doing is you have some distance you have to compute, and typically you do this in world space. So you don't do this in depth value space, but you have a 3D coordinate or a 3D point basically on the face mask that is stored on this pixel, and you compare it with the 3D point that is stored in the depth input image. So it's back projected into world space, right? And how do you compute a distance between 2 points? Well, there's a couple of options, and we actually talked about them. One thing you can do is we can do a point-to-point distance, right? It's just snapping to the next nearest neighbor and check the distance. But you can do also other things like point-to-plane distance, symmetric point-to-plane distance, and so on. Pretty similar what we have done in the context of an ICP, except now it's a difference between the rendered face mask and the respective rendered input image. Okay, now there's also like a couple of things I'm conveniently ignoring. You can also do the same tricks for ICP, for outlier removal, right? For instance, if the distances are too large, remove them and prune them. If the normals don't match, don't use those correspondences and so on. It's pretty similar than before for the rigid cases because this is just a standard data term. You have this photometric term and you have the dense depth term. Right? Yeah, and then you're combining these two, and you try to optimize for them. And what you will realize is this works really well if the face is already pretty close. So if the face is already rendered almost on top of the face in the input image, then these terms are pretty good. Then this works relatively well, despite not being super convex. You can, do a bit of course define and so on and make this work. So this works to a reasonable degree. But you first have to get a rough alignment in order to make sure that these re-renderings make any sense to begin with in the first place. And what people typically use is some sparse terms here. Maybe sparse is also not the ideal word. You can also call it a facial landmark term. And this term, basically what it's doing is you run kind of a facial key point detector. What you see here, you see all these red points here, right? Not my laser pointer, but the actual landmarks here in the face. You also have on the template model, again, we haven't talked about this in too detail, but it's straightforward, like just the template model that is used for the reconstruction or for the construction of the parametric face model has also landmarks. And then you just make sure that you for every point, for every landmark point here, you know where it is here. And then what you do is you compute a 2D image distance, like an L2 norm or so, in order to help the optimization. And in practice, this term is relatively convex. So it's much easier to optimize for because you have a one-to-one mapping by construction. So if you have a landmark detector here, you know exactly where every point that you detected here should be on the 3D mesh. So the landmark detectors, they might be wrong sometimes, right? They might be off by a few pixels. They're maybe not super accurate. But the rough high-level alignment, this one works pretty well. And there's a couple of options how to do landmark detection. There's traditional ones. There's a bunch of different existing handcrafted feature detectors here, but there's also very new ones like OpenPose is extremely popular. They use deep learning to detect these key points. There's MediaPipe, which is super popular, and so on. And OpenCV has a couple of them too. You can play around with those ones. And these are really important in this case to get close enough with the coarse alignment such that you can then later run a dense optimization afterwards. Right? And I conveniently wrote this here all in one line and have like one energy. But in practice, what you would do is you reweighting these terms. And at the beginning of the optimization, you typically only have the sparse term. So the sparse term initializes the whole thing. And once you're close enough, the dense terms kind of take over and you give more and more weight to the dense terms. Very similar to the dense bundle adjustment stuff we've seen before, except now it's done for faces. And if you think this is repetitive, then this is great because then you understood a lot of the concepts how to design these energies actually. Yeah, so you optimize sparse first, you get close enough. Once you're close enough, you get good correspondences for the dense ones, and then you give more weight on the dense terms eventually. Okay, and then there's another term here that I haven't talked about yet. It's this regularization term. And this is a prior that just says, well, don't deviate too much from the average face of our face model. What does it mean mathematically? Mathematically, this just means just sum over all of the face parameters, right? These are the face parameters P. And all we're doing here is we're saying, oh, please stay close to our average face. And in practice, what you do, you just assume sort of a Gaussian distribution here in this face parameter space, right? And you say, oh, like within the standard deviations or within 3 standard deviations, you shouldn't deviate. And practically speaking, what this means for the optimization, you just literally sum up the parameter offsets from the mean, and you just sum up the squared offsets here, right? This is very straightforward. It's just the measurement in parameter space of the face model. There's a few things maybe to consider is that different parameters might be or might have to be reweighted differently, right? So for instance, the expressions in the shape, they might live in slightly different spaces, so you might want to normalize those ones accordingly, and yeah, and so on, and the same with albedo and so on, right? But I guess you get the concept. So this term is just saying, oh, don't deviate, don't go too crazy in the face parameter space, make sure it's still kind of a reasonable face and don't deviate too much of it, And mathematically, how you're adding this is you just add a term that penalizes deviations from the average phase, so to say. Okay, so now is the slide that is the more math-heavy one. So brace yourself a bit. So now I want to go very quickly over the math terms over all the things what I've just told you. So now I've visualized all the data terms. Now here's the math part of it, right? So what we're having here in practice, we're having a bunch of terms that we're all summing up, and they're all being like weighted together. And we have these two here, geometry and color. These are the dense terms. This is our sparse term, which is based on landmarks. And this is our regularization term, which I said it's just summing up the phase parameters, which is the deviation of the average phase model in our parametric space. Okay, so let's talk about these ones a little bit, because this is really important, I think, that you understand it, what this means again mathematically. Okay, so let's talk about the geometric term. Well, first of all, we have our model. That's our model M. The model M takes parameters P as input. The model has I vertices. And what we do is, in this case, we're going over every vertex here. This is a little different to the previous slides, because in the previous slides, I told you we're going over every pixel. You can do it either way. Both of them is valid. For the sake of simplicity here, I is a vertex, but I could also be the pixel of the rendering. But then the I would change every time you re-render, because you're getting a different number of pixels. Okay, but that's not the most important thing here. The most important thing is here the parts inside of the zone. Okay, so the dense geometric term, it has two parts. It has a point-to-point term, and it has a point-to-plane term. I've said this before, and these two terms, they can be reweighted accordingly. I mean, these weights are missing here, but you can imagine just adding a lambda here, reweighting those two. Okay, so what does it mean? So what you do is you're rendering the whole thing. You're getting a rendered vertex here. This is why it makes it a little easier to think about it as a vertex. You could also do it based on a pixel, but then there's a barycentric interpolation, then it becomes a little bit more complicated to write it down. That's why I cheated and wrote it in a vertex form here. But this is a vertex that is determined. Its position is determined based on the parameters P, and you're comparing it by looking up the depth map at this position. You back projecting it. Sorry, you have the 3D point of the vertex, you're projecting into the image, and you're looking up into the depth map. This is what this is doing, right? This is a vertex in 3D space. You're projecting into the depth map, and then you're looking up the depth map value, and then you're getting a position at this depth map value, and you're comparing it with the vertex position. This is just this point to point. Now you do the same thing with point to plane, except you multiply here with the normal. So you have this dot product with the normal, and then you have the point to plane distance. And what you do is you just sum these ones up. Again, there would be a weight, a lambda weight or so here, but this is our dense term. And we're doing this sum is done over every vertex of the mesh, but it could also be done over every pixel in the rendering. The reason why I wrote it down here as a vertex, it's significantly easier to write it down, because if it was a pixel, we have to go first from rendered vertices to pixels, and then it's a little more complicated because you have this barycentric interpolation. We'll talk about this in a few slides later, actually, how this works in detail. Okay, for the color, same idea. You go over all vertices, you check out the model, based on the parameters P, you're getting a color value here, and you do the same thing now. You take this 3D point of the model based on the parameters P, you project it in the color image, you look it up in the color image, and then you compare the distance in Rgb space. In this case, this is a 2 norm, but we're comparing the colors at the surface point I with the respective observation in the image where this point was projected to. Okay. Again, this is an L2 distance. In practice, there's many different options here. So for the top part, by the way, there's point to plane. That's more or less it. Here, for the color terms, you have many different options. You can go and do differences in Rgb space, you can differences in lab space, HSV space, and so on. And again, you can use all the different norms, not just an L2 norm, you can also use L1 norms. In practice, L1 norms are better, they're just nastier to optimize. So it's a bit of a compromise, what I said before. Okay, these two are our dense data term. This is clear, I think, right? And now we're going to talk about the sparse terms. This is our landmark term. So this I here, this is important. This I here is not going over every vertex, actually. Now, this I would go over every marker location on the face. And then what we do is you check the marker location based on P. Then you feed it into pi to project it in the current 2D image. And then you're comparing this CI here is a 2D position where the respective landmark was detected. And this is a 2 norm between 2D points. Right? This is always important to figure out the dimensionality here. This is the difference between points in 3D. This is the difference here between color values in RGB space or whatever. And this one here is a difference in landmark coordinates in 2D. Yeah, it's a little bit of a bad writing. I should have not chosen I here. I is not the right mark. This is not the vertex in a sense, right? This is basically for every landmark on the mesh projected into 2D. That's what's being done here. And compare it where the coordinate in the input image should have been. It's the 2D location of the projected marker position. Okay, and this loop here typically goes over, I don't know, like 50 to 100 markers, whereas these two loops at the top, they go over everything what we have. It's like thousands of vertices or even like hundreds of thousands of pixels, right? Okay, and the last term is this regularization term, right? So we have here 3 parameters. We have alpha, beta, for the respective identities, right? And these ones are being divided here by the standard deviations. But all you're doing is here you're summing up square terms and you want to minimize the deviation from the average phase. And here this last term is for the expressions here. These delta blend shapes or whatever you're going to use them, they also going to just be squared here, and they're going to be also divided by the respective standard deviation, and we're trying to minimize the deviation from the average phase. There's also a bit of an argument whether you want to use an L2 norm here. Most people use those because this works typically pretty well and it's easy to optimize and gives plausible results in practice. Right? Okay, so this is the math behind it. Sorry a bit for my sloppy notation. I just noticed there's another typo here. This one should be a delta here, by the way. And not a gamma. But yeah, these are the expression parameters that are here actually in practice, right? Okay, but then what we have to do, let's go to the simplified version again, right? We have the dense terms, we have the sparse terms, we have the regularizer, data terms, and priors. And now what we want to do is we want to find the optimal parameters P that minimize this energy. And this energy now is an optimization in a high-dimensional space. But most of these terms, depending a bit which norms you're using, I wrote down all 2 norms that makes it a little bit easier. But this is basically just a nonlinearly squares problem, right? So we just have square terms here that are being added together, and we want to minimize those ones. And we have already talked about this in the previous lectures to quite some degree. Now we want to figure out how do we do optimization here. And to get this done fast, you want to use a second order solver. In this case, we want to use Gauss-Newton to get this done very fast, right? And here's a quick reminder how the Gauss-Newton works. So for the Gauss-Newton here, here again, we have our energy, we have our parameters P, we have these squared residuals. And what we do is we have this iterative update rule. So we have this starting with Pn in the nth iteration. We are subtracting JTJ inverse times JTF. So this is the gradient, right? This is JTJ, this is the gradient, and this is this delta vector here. So we bring this one here to the other side instead of having to do this complicated inversion. So we have JTJ times the delta vector is equal to JTF. Again, this one here is the gradient. And now what we want to do is we want to solve this this linear system in every iteration. And then we're getting the update and then we iterate accordingly, right? So this is just standard Gauss-Newton. Please compare what you're seeing here with the slides in the optimization, what we talked about, where we talked about how Gauss-Newton, Lemberg-Marquardt solvers, and so on are doing. You could have used Lemberg-Marquardt, by the way, here too. I'm just using Gauss-Newton for simplicity. This is also what a lot of papers use in practice. This is like a canonically squared problem, so this works in practice pretty well. Okay, so what does it mean again? Just again as a reminder, these terms here, these residual terms, this is basically all the stuff we've discussed before, right? So we have here the distances in depth space, we have the distances in color space, and we have the distances in landmarks, and we have the regularizer that says don't deviate too much from the average phase. Okay, now what we would have to do right now is from this function f here, right, we have to compute the Jacobians. So we have to compute the Jacobian of f, and I'm going to try to do this a little bit visually right now. So if we're doing this, we're getting something that looks like this. This is our Jacobian of f with respect to the parameters p. Okay, so now here we have rows and we have columns. Sorry, we have rows and we have columns. So in our Jacobian matrix, every row here has partial derivatives where each entry of the row is with respect to a different parameter p. Okay, so now here we have p0, p1, p2, p3, p4, and so on, right? So we're having the number of columns here, the number of entries per row, is equal to the number of unknowns that we're having in our parameter vector p. In this case, we have pn. We know roughly how large that is. We did this in the last lecture, which was basically the dimensionality of the parameter, which was exactly the dimensionality of the parameters of our phase model, right? Okay, and then what we have here is what this is like. What is just this difference here between the depth terms? This is like one row per dense entry in the depth term. Remember the sum that we went for all of the depth values that we projected? We're going to have one row now for each of them. Okay, and then we do the same thing for the color. Again, one entry in each row goes to every unknown in our P. So we have these partial derivatives. And then what we have is we have one entry for every reprojected color value here, either vertex or pixel, depending on how you do it. So we have quite a few. We have in these two dense terms here, we have quite a few rows that we have to consider, right? So it's a pretty big term. And then what we're doing afterwards, the same thing goes for the landmarks. Again, we have one row for each landmark, and we're going to have one row here for each parameter. Actually, this part here at the bottom is square, right? Because it's number of unknowns per row, and it's number of unknowns in a sense times rows, because we have one residual term per p entry, which we want to regularize with this square. Okay, so computing these partial derivatives, some of them are easy to compute, some of them are not so easy to compute. The easiest one here at the bottom, this regularize is straightforward. It's just the sum of square terms of the unknowns, right? That's easy. This one here is also easy to landmark. It's just the difference between 2 points. These 2 points are given. It's straightforward, right? And we know basically like 1 point is parameterized with respect to p, so we know exactly how to compute the partial derivatives here. For the depth, it's also relatively easy. We know how the positions in 3D are being parameterized with respect to the parameters of the model, so it's also straightforward. Now this part here, this part here is not so straightforward now, because now what we would like to do is we would like to compute partial derivatives of the synthetic rendering with respect to the parameters p. In other words, I would like to know if I change my parameters p in a certain way, how are my 2D parameters, how are my 2D values actually changing in Rgb space, right? Okay, so what this means in practice is we need to differentiate through the rendering process, right? So I would like to understand if I re-render, how do my models change respectively? And this is what I said, it's a differentiable rendering process, right? So, and I'm going to talk about this one in a little bit of detail, because that's a thing that is not just relevant for this part here. This will be relevant to many other applications you're going to use in practice if you ever want to do anything with analysis by synthesis, right? This is not just for phase models relevant, but in practice this is also relevant for other models as well. Okay. Right. Okay, give me 1 second. I need to turn off my AC here. All right. Okay. So now we have to talk about the differentiable rendering. How does it work? Well, in this case, the rendering is basically taking these parameters p here as input, constructs the parametric model accordingly, like parameterizes the mesh, right? It feeds it into the GPU. The GPU renders something out of it. And what we would like to know is, for instance, well, for this pixel, for instance, how do we compute the partial derivative? In other words, how is this pixel being affected with respect to the parameters p that we fed in originally? Okay, for that you have to understand the rendering process a little bit. So the way it works on the GPU is everything is a triangle, right? So this mesh here that we're having here as input is a set of triangles. And what happens here is we have to feed these triangles into the rasterizer of the GPU. And what the rasterizer of the GPU is doing, it's figuring out which pixels are being covered by that specific triangle here. Right, so here's our pixel grid. This is our raster grid. This is this infamous triangle that I just mentioned. And now the rasterizer is going to figure out, okay, which pixel is going to be covered by this triangle. And it does it actually for all the triangles very fast and all in parallel. This is what the graphics cards are doing for you. Okay, so let's just say the graphics pipeline does that for you. Afterwards, the graphics pipeline now has to figure out a way to assign a color to this pixel here. And this pixel color here is dependent on the original triangle. To be more precise, what the rasterizer is doing here, once it figures out which pixel is covered by the triangle, it checks which vertices here were involved in this triangle to begin with. So we have here, we have three points P. These are the vertices of the original mesh that we used. And what the rasterizer is now doing, it's finding an interpolation between these three vertices and figures out how to interpolate these three vertices for this one pixel. And when I say interpolate these vertices, what it actually is doing, it's interpolating the color values, the attributes of these points, in order to find the color value for this pixel. That's what's happening here right now. And this is the formula. It's relatively straightforward, right? So we have three color values for the three vertices, CPI, CPJ, and CPK. And now we have three coefficients, alpha, beta, gamma, that figure out how to reweight these vertex colors in order to find the color for this one pixel. And this is a linear combination of vertex colors. And in practice, what the rasterizer does for you here, it does barocentric interpolation. So it knows where's this pixel relative in this triangle, and then it figures out a barocentric interpolation, uses the barocentric coordinates, to interpolate the attributes of these vertices, including the vertex colors. And this is what's happening here. These alpha, beta, gammas are nothing else but barocentric coordinates. They're given to you by the DirectX OpenGL pipeline, and based on those ones, you can interpolate these color values here of these vertices in order to get the final color for this pixel. Now, if you want to make this whole thing differentiable, what you would have to do right now is, remember what I want to do. I want to figure out for this one pixel the partial derivatives with respect to the original parameters P of my model in 3D. So I know how these vertices here are defined by the parametric model P. That's what we've done before, right? And now what I have to do is for this pixel, I have to memorize first which triangle is it. Based on this triangle, I know which of the three vertices is it. And based on these three vertices, I know the barocentric interpolation, because I can also store alpha, beta, gamma here, which is what the graphics pipeline did for me. And then I can go back to the original parametric model, and I know this pixel was affected in a certain way by the parameters p, and I can do this partial derivative accordingly. And the way you do this in practice, you store this information during the forward rendering pass. In other words, you just render the 3D mesh. You store for every pixel which triangle this pixel belongs to, the triangle ID. You store the 3 vertex IDs, and you're storing the 3 barycentric coordinates. That's what you need to know. Okay, and once you have it, then we can go back to our parametric model P. And this is what I'm doing here right now. As I mentioned, these colors of these vertices, they are determined by the parametric model P, right? This is what our P tells us. And we have this for each of these vertices. The barycentric coordinates are given. And what we want is, how is this color at the pixel P here? How is it affected by these parameters P, right? And then all you do is you just do a computed partial derivative, right? So the partial derivative of this thing here is then the partial derivative of all of these 3 points. And these are partial derivatives of the parametric phase model accordingly. Okay, and it's actually relatively straightforward to do that because this is all pretty much supported in the graphics pipeline. You just need to write a pixel shader accordingly to store the triangle IDs and the vertex IDs and the barycentric coordinates. And then this is relatively straightforward. And then you have your favorite differentiable renderer with the forward rasterizer implemented. Okay, next step, we're gonna go back. And now we have our Jacobians, right? So now this whole differentiable thing was this part here. It's like how to differentiate in this analysis by synthesis approach through the RGB comparisons of the renderings with respect to the observations we had in our image. One thing you can already guess, this whole thing here is actually quite computationally expensive. It's not super fast because the dimensionality here of this matrix is quite high. How high is it? Well, this one here, the number of parameters is the number of entries per row. That's easy. That's maybe a few hundred. But here we have a few, maybe even a few 100,000 rows here, right? Depending on how many points we're considering here for these dense terms. This is really the limitation. These 2 terms here, they determine how many entries we're going to have in our Jacobians. Okay. All right. So how do we do it fast? The first thing we're going to do is what we always going to do. Whenever you have photometric terms, when you have dense terms, you're going to reduce the workload by doing some coarse-to-fine optimization, right? What does it mean? Well, instead of using the original image, we're going to downsample. We're going to downsample, and so on. And what it means is, well, on the lowest resolution, we're doing first the optimization there. It's not perfect. It's not going to be as accurate as on the high-res, but it works a lot faster because we have a lot fewer residuals to deal with here. Then we sample up, we go to the next level, we do the same optimization with the initialization from here, we continue on this hierarchy level. And only then we're going back to the original level. So this coarse-to-fine idea, also a thing, not just relevant for faces. This is a thing people use all the time for all kinds of different works if they want to get things fast. Interestingly enough, it's not just for getting it fast. This also helps massively in terms of convergence. And by convergence, it's not just how fast you converge. It's basically a convexification, right? Because that makes it a little bit less brittle to small outliers in the color because you're downsampling it and so on, and this helps in practice. Okay. Right. So now what we can do is we can do this coarse-to-fine optimization. We know how to compute all the partial derivatives. The last thing what we have to do is we have to do it pretty fast. If you want to do this fast, you do this on a GPU. You spend a lot of time writing your custom Gauss-Newton solver, and then you get real-time performance. And this is kind of cool. So you can actually get this to work in real time. And it takes a little bit of effort to implement it, but it's, I think, kind of cool. So nowadays, you can do this also with like things like PyTorch and so on. They are helping you with a lot of these things. They also have, in part, the differential renderer. So this helps to some degree. But if you want to be really fast, you have to probably still implement this in CUDA or HLSL or something like this in order to get fast performance. But now is the time. Now is the big moment. We've done a lot of theory right now. We've talked about the energy terms. We've talked about the residuals. We've talked about the Jacobians. We've talked about how to compute partial derivatives. We've talked about differentiable rendering. Now we want to see our final results, our reward of finally doing some facial performance capture. And this is a work that has been done. This was done by Justus Thies. He was a postdoc actually in my group. He's been working on this for a while, and this is 2015. Take RGBD input. Here's the RGB image, and this is the respective reconstruction of him. And this works in real time, actually, right? So I think it's kind of nice. It's pretty robust. It can deal with like glasses and so on, but it can reconstruct this face model in real time, and you get quite robust performance with respect to any outliers and so on. And I think that's kind of cool, and it's nice. And what's interesting is we're not just reconstructing here the geometry, you're actually reconstructing everything in the parametric face model. So let's have a look here. This is the practical input. This is the RGB and the detected landmarks. This is the depth data. This is the reconstructed geometry. This is the reconstructed albedo. And this is the reconstructed texture on top of it. This is the geometry overlaid on the output. So you see it follows very nicely the motion of the input. And the very interesting one is actually this one in the bottom right, because this is a re-rendering of this textured model on top of this input. And if you cannot see a difference between this one here and this one here, then we've done a pretty good job in the optimization, because that means that every pixel here coincides with every pixel here. If you're looking very closely, you can still see a few artifacts, but it's pretty close actually. So this one essentially is the optimized version with the texture on top of it, re-rendered on top of the input. And if you can't see the seams here, if you can't see the face model anymore, that means this is pretty good, because that means every pixel of the re-rendered model coincides with input observations. And that's kind of cute. All right. I think it's cool. All right. I mean, you can already admit, I mean, this is cool because this is a re-rendering here of the reconstruction on top of the input, and that looks kind of like the input. So we've done a good job at the reconstruction. Okay. So now I want to relax the whole problem a bit. So admittedly, you could argue, well, this is facial performance capture, but it still uses the depth data. What happens if we're just getting rid of this part here, right? If we don't use the depth as input. And in fact, you can do that. And it works actually still remarkably well. The only thing what you have to do, you have to go in a pre-processing step. You have to basically figure out the shape of the identity of that person first. What does it mean? Well, instead of using just one input image, you're taking 6 input images. And for these input images, you're jointly optimizing the energy, right? So what you do basically is you have this energy that is summed up of all of these frames, where you have one energy per frame, but the parameters P between those are shared except the expressions and the poses and the lighting. But what's shared between those, between all of these images, we know that our albedo coefficients are the same, and we know that our shape coefficients are the same, right? And if we're having multiple frames, we're adding more residuals because we have more reprojections. But we don't add more unknown parameters for the shape and for the albedos because we know it's the same person in the entirety of these videos, right? And then we're just jointly optimizing in this kind of like bundle adjustment fashion, right? We're taking all frames at the same time as input. And then you're optimizing for the identity first. And once you've solved for the identity first at test time, or whatever you call it, at online time, then you only have to optimize for the poses, for the expressions, and for the illumination. The illumination is a question whether you want to resolve it. In practice, probably yes, because the lighting might change. Like somebody turns on the switch, right? Then the light switch, then things change. But at runtime, then you don't have to optimize for the identity anymore. And if you do this, you're basically adding enough constraints such that you can still go ahead and estimate the expressions, the illumination, and the poses just with the RGB video feed. And this is what you're seeing here. Okay, so here we see the reconstructed RGB or albedo. Here we see the reconstructed, well, unfortunately PowerPoint for me like sometimes shifts these videos. I'm gonna show these again. right? So you see, this is a really nice tracking. So every pixel here is pretty much coinciding with every pixel here, and we get a very, very good reconstruction, actually. And again, this is kind of nice because it now only works with RGB input and doesn't even need the depth input anymore. Okay. And I think this is a really cool result because this is a real-time face tracker right now that reconstructs a high-quality model. We have all the parameters P being optimized in our face model. And we can do it in real time, right? So we get super accurate reconstructions, we get it in real time, and we have all the information about expression, identity, albedo, and illumination of this respective person, right? Okay, so let's summarize what we've just done. So I wanted to also show a few error terms that you get a bit of a feeling what's going on here. Okay. If we're doing this parameter optimization, we have here input data. We have different types of input data. We can only use RGB, we can use RGBD, and we can also only use the facial landmarks. So these are the different comparisons here. This one is saying just use facial features, means facial features for landmarks. Features plus the RGB term, features plus the depth term, features plus color and plus depth term. Fair warning, without the features, none of them would work because you need this initial coarse alignment. So the features make all the sense to have them to some degree. And what we are seeing here are a bunch of plots. This is the initial overlay. This is the geometric error with respect to the ground truth. This is the photometric error with respect to the reprojections. Right? So let's have a look here. You see already here, for instance, the face template is slightly shifted. So it doesn't quite align here and is not perfect. And you see this here in the error plot of the geometry. But it's just not perfect, right? And you also see it with the photometric reprojection. You see that, for instance, here in that region, here the tracking doesn't quite work out if you're reprojecting the colors. And the reason for that is the dense term is missing here in order to get a very fine scale alignment. So you need the dense terms. Now, if you add in the RGB term, what happens is the photometric error goes pretty much to 0, which is great, right? In this case, we have very good photometric reprojections, but what's going to be wrong is the absolute depth. And this is what you're seeing here. So the absolute scale of the model is slightly off. In other words, what's going to happen is the shape, in a sense, is a bit compensating for the wrong depth then, right? So color is good for reprojection, but it's not that amazing for absolute metric reconstructions. If you're using only the depth, it's the other way around. And the metric reconstruction is pretty good, but the photometric term is not that great. For instance, here you have similar artifacts. And only if you use both of them, color and depth, you're getting both of them to be smaller. By the way, this error plot is not a huge surprise. This one is basically visualizing the cost function for the geometry. This one is visualizing the cost function for the photometric term. And if you have no photometric term, then you have a high error. If you have no geometric term, then you have a high error here, right? So that kind of makes sense. But I wanted to make you aware of, like, okay, these different terms, they have different results and they cost different outputs at the end of the day. Okay, so the other thing what's important is actually the face model, right? So for instance, what we've been talking about is a model that looks like this, right? This is the model where we have a lot of vertices, we have a very dense model, we can use those, we can have these dense terms. If you don't have a dense face model, you can't have dense terms, and then with only sparse energies, you can't get as fits, right? So this makes quite a difference, like how dense should this model be, how much detail do you want to have, and so on. So this makes quite a big difference. And the last part is, in the stuff what you have just seen is the runtime requirements determined based on the dense model. If you have more residuals, everything becomes slower. So the landmark tracking is straightforward, but it's not super accurate, right? But the landmark tracking you can do on a phone. Every phone can do this today. The dense terms, even today, I mean, these papers were a few years old. Doing it on a phone with the dense terms is probably doable now, but you probably don't want to spend that much energy on it. So it depends a little bit on the application. So you have to be very critical about the runtime requirements here, right? And this brings me to the last part. There's a lot of different applications for face reconstruction, for face tracking. Do we need a dense reconstruction or not? Is it enough to just use landmarks? Do you need the RGB terms? Do you need the depth terms? So this is something you really have to consider when you're designing the method accordingly, right? I don't want to just say, oh, there's one method here, but like pick carefully which terms you need for the respective application. Okay, with that, I would like to conclude the phase tracking and the parameter estimation. But now I wanted to talk a little bit more about the applications, what you can do with it. And one application that I'm particularly very keen on, which I think is super cool, is facial reenactment. So the idea basically is we would love to take a video feed and would love to create kind of a virtual avatar that we can then control possibly by another person. And this is called facial reenactment, right? So my face could be controlled by somebody else, right? This is my goal for retirement, by the way. I just want to have an AI basically make sure these lectures can be automatically generated. So that will be cool in the future. Working on this, but it's not quite there. But yeah, so the idea is basically you have this virtual avatar and you can animate it, and this is done by facial reenactment, right? So in this case, we're having two actors. We're having a source actor. He's going to provide the input of the control. And we have a target actor whose face we want to manipulate. So we want to build an avatar of him, which is shown here. And we want to track his face to control his face, right? And the way this should work in principle is based on the pipelines that I've just shown you. And what happens is essentially we are reconstructing the face of him. We are reconstructing the face of him. And then we want to transfer the expression parameters from here to here. And I want to show you how this works. So this is the input. What we can do is we can go ahead and reconstruct his face, right? And what that means is when we're reconstructing his face, we're taking here Rgb Data input, we're getting geometry reflectance and textures, we're getting this nice re-rendering, and we're getting the overlaid geometry. And now what we're doing is we're doing this for both source and target actors simultaneously. So we're running this dense tracking for the source and for the target accordingly. And what we're getting is we're having this parametric face model, right? So we're getting all of the parametric face model parameters for the source and for the target respectively. So we're getting expression, pose, illumination, identity for both of them. And the idea is that from the source actor, again, that's the one that should control the other one, we're now taking the expression vectors here, right? So the expression vectors, and we want to feed those ones into the target for the reanimation, right? So instead of re-rendering the target with the original expressions, we now want to use the expressions from the source and re-render the target with the expressions from the source instead and get this as output, right? So his open mouth, in a sense, these expressions coefficients that from his open mouth are being transferred to him, and then the mouth will be open here. So this kind of edited the image right now. Yeah, in practice it looks like this, right? So what we're doing here is we have here the input source, the input target. We're tracking all of the face parameters here. We're tracking all of the face parameters here of both of them. And what we're doing right now is of the source, we're taking the expression parameters here, right? So we're taking the delta parameters. And for the re-rendering here, for the reenactment, we're using these delta parameters here to re-render his face, but with his expression parameters. Right? This is what's being done here. You see, he's moving his mouth and he's not moving his mouth, but his re-rendering is also not moving the mouth, which is kind of nice. This is why we have this facial, this parametric face model, because we can do this expression transfer very nicely. Now, this one here is not yet photorealistic. There's a bunch of things missing now. We have to now figure out how can we take the stuff what we've done here with the stuff from the expressions here and can re-render this accordingly, right? So due to the changed expressions, we have to re-synthesize the target face, and we have to composite it though into a new output video. And there's a few things that we have to fix here that are not part of the face model, which is a bit unfortunate. The face model just is the face part, but there's a few other things we have to edit. And that's what we have to do. We have to basically figure out, so we have the modified face model, right? We texture it, that's straightforward. Now the problem what we have is we also have to figure out something about the mouth. In this case, we're using a little teeth proxy that we rig non-rigidly with respect to the base mesh. We also have to figure out something with the background of the mouth, because that's moving too. We have to synthesize something there. And then we overlay it on top of the original RGB input. The way the mouth proxy is set, this is just the 3D model that we rig with respect to the face. The mouth background, this is just a non-rigid warping of this texture based on an RF term. So it's a non-rigid warping with RF of this texture warped on top of the input here, right? And then you're getting this here as output. Well, first you get this one, and then you composite it with the background, and then you're done, right? So the few small tricks that had to be done. I want to show how this works. It looks kind of funny. So this is this teeth proxy that I promised, right? This is the input. This is the source expression that is being transferred here. This rigs the template here. This is the mouth interior that is non-rigidly warped on top of it. And this is overlaid on top of the input. Right? So this is the input video, and this is the reenacted output. So it looks kind of cool. Now you can see how the reenactment is already working at this point. Okay, here we have a few more results. Again, source actor, target actor. So her expressions are now being used to animate him as a target sequence. Same idea again. Target actor being controlled by him here. And you see that, you know, eyebrows, stuff like this, all being animated here. Okay, the nice thing is this runs in real time. So now you can do stuff like this. So here are two prime sense sensors. These are RGB sensors. They're reconstructing both faces. He's talking, it's his video, but his expressions are being transferred to him right now, right? Same thing here. She's the driving actor right now, and her expressions are being transferred to him here. Same thing here. Now he's the driving actor, and his expressions being transferred to him. Okay, so there's a few weaknesses basically of this whole thing still. One thing is pretty funny. This teeth proxy, I think, which is a little bit hilarious. Basically, everybody has the same teeth afterwards. So this is the teeth proxy. It looks also over white and super unnatural in a sense. If you know the person, like him, you know very quickly this is not him. If you don't know him, it's actually a little bit harder to do. But I think there's probably better ways to do this. And one option is to do this image-based, and I'll show you how this works in a second. The other thing is, this one here still requires an RGBD sensor. It would be cool if you can do the whole thing without RGBD, but rather using a video sequence as input, because then you can do this on any arbitrary YouTube video and can just do arbitrary face editing. Okay, let's talk about the mouth. For the mouth part, what can be done is basically you build a mouth database of this one sequence, and then you do a non-rigid warp, basically with RF and a bunch of image compositings, and do this image base for the mouth. That way, you actually get a mouth that looks like the respective target. It's not going to be so perfect all the time, but it looks actually pretty reasonable if you do it right. I'm not going to go into all the detail here, but I think it's kind of this is kind of the improvement from this teeth proxy, which I found a little bit hilarious. Now you can basically do this on an image-based way. You take the mouth here, and then you can do a re-rendering of the mouth. For the second part, what we've seen for the RGBD part, we've already seen it. If we are taking the depth away, we're not getting metric results in terms of the face sizes for the reconstruction. But we don't need it here. That's the fun thing. Here we just need the reenactment on top of the input, right? And in this case, we can just leave away the depth. And it turns out this works reasonably well. You can do a few things to get the tracking a bit better if you take the depth away. One thing what we realized is you can take away the depth and do RGB only. But then for the RGB only, you rather want to use an L1 norm for the RGB distances. That works a little bit better, but it requires a bit more effort on the optimizer. In this case, you have to use an iterative free-weighted nonlinearly square solver. That works better and gives better results, and then you can do it on YouTube videos. And this is a result I want to show here. This is, I think, probably one of our most popular papers. This is this face-to-face paper. Probably some of you might have seen it. So with this paper, you can now basically do full reenactment and full video control. So the single webcam, he's being recorded, and he can reenact him here in the respective target video accordingly. And this, again, works in real time, and it works on pretty much any arbitrary video, as long as you don't have like any crazy occlusions in the face. And I think it looks actually pretty good. And this one is done 2016. So this one was still done without any deep learning. This is like a pure reconstruction, re-rendering, analysis by synthesis approach in order to get this full facial reenactment results. Here's another close-up. Again, here's the source actor, and here's the respective reenactment. So he's controlling his face in real time. All right, with this, I'm more or less through today's lecture. I hope this was kind of a cool application, because this has, of course, a lot of interesting inspirations, what you can do with this kind of technology. There's also a bit of an ethical consideration, so of course we have to be careful how we use it. That's something maybe I would like you to think a little bit about as part of the reading homework. And I would like you to have a specific look at these two papers. They're both from Justus Thies. I think they're really cool papers. This is something you have to look at. So it's this real-time expression transfer paper. That's the first one. That's basically the tracking with RGBD and the expression transfer, and the face-to-face paper that makes it then happen without any depth input again. Okay, and yeah, in the next lecture we're going to continue with more tracking and reconstruction. We're going to look a little bit at bodies and hands, and I hope you enjoyed it. Thanks a lot for tuning in, and hope to see everybody next week. Bye bye.